Well, I'm going to calculate the electric field created by a disk of uniform density of charge, but before I will calculate what is the electric field created by a ring at a point on the axis that is perpendicular to the ring and passes by the center of the ring. Once I have the electric field created by that ring, I will integrate from a ring of radius 0 to a ring of radius capital R, and then that way I am calculating the electric field created by that disk. So let's calculate the electric field at this point P created by a ring of charge. In order to do that, I'm going to use the definition of electric field, and I will look at a tiny chunk of this ring of charge and calculate first what's the differential of electric field created by that differential of charge. So this is just a very thin ring which has a charge density, linear charge density of lambda, and which that lambda is going to be the total charge Q divided by the length of that ring, which is 2 pi r, and that little differential of ring will create an electric field on that point P pointing in that direction. That's the differential of electric field. But because opposite to that little differential of charge, there is this other differential of charge opposite, will create exact same electric field pointing that way, and the vertical component will cancel, and then only the perpendicular, the one in the x direction, is going to survive. So this is going to be d e sub x. So because of the symmetry of the problem, only the electric field, the differential electric field in the x direction, is going to survive. So I'm going to calculate the tiny differential of electric field by that differential of charge, and then project into that axis. So I will call this angle theta, which is the same as this theta. The radius of the ring is r. The distance from the ring to this point P is x. So the x-axis goes through the center of the disk and is perpendicular to the disk. So this angle theta, for example, the tangent of theta is this side, which is the radius of the ring, divided by this other side, which is just the position x. The sine of theta is going to be the opposite, which is again r divided by little r. I will distinguish the capital R as the radius of the ring and the little r as the distance from the differential of charge, the point I'm calculating that electric field, and the cosine of theta is going to be the contiguous side, which is x, divided by the hypotenuse, which is r. Now, what is the differential of electric field? Well, the differential of electric field in the x-axis is going to be 1 over 4 pi epsilon naught, the differential of charge, divided by the distance r, little r squared, and then projected. So this is the differential of E. Because I want the differential of E in the x-axis, I have to project, so I have to multiply by the cosine of theta. Cosine of theta. Now, what is the differential of charge? Well, the differential of charge is the charge density multiplied by the tiny differential of length that we have here. So the differential of length, this tiny differential of length, is going to be... Here I have to find a variable that is suitable for integration. In this case, dl. L is not a variable that I can integrate, but if I change that for something like phi, for example, an angle phi that I can integrate from 0 to 2 pi, then that's going to be very helpful. This is lambda, and the differential of length is the radius r multiplied by this differential of angle, which I will call phi. Is different from this other angle. So differential of phi. And the total charge is just the differential of charge integrated from phi is equals to 0 to phi equals to 2 pi. So this is the integral of lambda r d phi from 0 to 2 pi, and that is lambda r are constants, and the integral is going to be 2 pi, which is the same as we had here. 2 pi r lambda is equals to q. So that is the differential of charge. So I'm going to substitute it here now. So dq 1 over 4 pi epsilon naught dq is this lambda r d phi, lambda r differential of phi, divided by this radius square, and the cosine, which is x over r, over little r, by the way. Now, I have r to the power of 3. This r is a constant. It's always the same for all of the differential of charges. X is this fixed distance, so everything here is constant except for the angle. So I'm integrated all along who is creating that electric field, which is the ring. So I'm going from this d phi from 0 to 2 pi. Now, if I want to calculate the total electric field on the x-axis, that is the integral from phi equals to 0 to phi equals to 2 pi of this differential of Ex. Now, this is the integral from 0 to 2 pi of 1 over 4 pi epsilon naught lambda Rx over r to the power of 3 d phi, which I take all the constants out of the integral, 1 over 4 pi epsilon naught lambda Rx over r3 integral from 0 to 2 pi of d phi, and which is just 2 pi. So this is 1 over 4 pi epsilon naught lambda Rx over r to the power of 3 2 pi. So that is the electric field created by, in the x-axis, created by this ring on an axis that goes to the center of the ring and is perpendicular.